For as long as humanity has gazed at the night sky, we've asked not just what is out there, but how it all began. We've mapped constellations, charted the dance of planets, and decoded the light of distant stars. But beneath every discovery lies a deeper question. What was there before the beginning? Before galaxies? Before stars? Before time itself? Was there something? Nothing? Or was the very idea of before meaningless from the start? The Big Bang Theory has given us an origin story for the universe. 13.8 billion years ago, all of space, time, energy, and matter emerged from an infinitely dense, unimaginably hot state. But that's not the end of the story. It's the beginning of a mystery far more profound. Because if the Big Bang created time, then what does before even mean? And if time didn't exist, can we even speak of a cause? These aren't just riddles for philosophers. They are the frontier of modern cosmology, where the laws of physics stretch to their breaking point, and our best theories whisper of realities beyond imagination. To understand what might have come before, we first have to confront the limits of what we know. The Big Bang isn't an explosion in space, it's the emergence of space and time. There was no place for it to happen, no moment when it started, because space and time were born in the event itself. This is why asking what came before feels so paradoxical. It's like standing at the edge of a cliff and wondering what lies beyond the edge of existence. Our intuition fails us. We're used to cause and effect. Something happens because something else happened first. But if time began with the universe, then there was no first. The concept of before dissolves. And yet, the human mind refuses to accept silence. We keep searching, not just for answers, but for a framework that makes sense of the unspeakable. One of the most elegant attempts to resolve this comes from quantum cosmology. In the 1980s, Stephen Hawking and James Hartle proposed the no-boundary condition, a model where time, at the quantum level, behaves like a dimension of space. Imagine the universe as the surface of a sphere. As you move toward the South Pole, the lines of latitude get smaller and smaller until they converge at a single point. But there's no south of the South Pole. In the same way, as we go back in time toward the Big Bang, time gradually becomes space-like, and the singularity vanishes. There's no sharp beginning, no edge, just a smooth, curved geometry where time as we know it emerges from a timeless quantum state. In this view, the universe doesn't have a first moment. It simply is, like a mountain rising from a plain, with no cliff to mark its start. It's a radical idea, but one that avoids the need for a creator or a prior cause. The universe becomes self-contained, needing nothing outside itself to explain its existence. But what if time did exist before? What if the Big Bang wasn't a beginning, but a transition? This is the heart of the cyclic universe model. Some versions suggest that the universe expands, eventually slows, and then collapses in a big crunch, only to rebound in another Big Bang, a cosmic cycle repeating over trillions of years. Each cycle resets the universe, wiping the slate clean. But newer variations, like the conformal cyclic cosmology proposed by Roger Penrose, suggest something more subtle. In his model, the far, far future of our universe, when all stars have burned out and black holes have evaporated, becomes indistinguishable from the hot, dense state of the Big Bang. The extreme scale differences fade, and one eon ends as the next begins. Penrose claims to have found evidence in the cosmic microwave background patterns of concentric circles he calls Hawking points, possibly echoes of black hole collisions from a previous universe. The scientific community remains divided. Some see it as a bold reimagining of time. Others argue the data isn't statistically significant. But the idea lingers. What if our universe is just one chapter in an endless story? Then there's the multiverse, the idea that our universe is just one of many, perhaps an infinite number, each with its own physical laws. In eternal inflation theory, space-time undergoes rapid expansion in some regions while stopping in others. Each region where inflation ends becomes a bubble universe. Ours is just one bubble, floating in a vast, ever-expanding quantum foam. In this scenario, the Big Bang wasn't the beginning of everything. It was just the moment inflation ended in our local region. The larger multiverse could be eternal, with no beginning and no end. Some versions of string theory suggest these universes exist on higher dimensional membranes or brains floating in a bulk space. A collision between two brains could have triggered our Big Bang, like two soap bubbles merging. It's a compelling image, one that turns the origin of the universe into a cosmic accident in a much larger reality. But here's the catch: if other universes are beyond our cosmic horizon, we may never observe them directly. The multiverse, for all its elegance, risks being unfalsifiable outside the reach of science. Or does it? Some physicists believe there could be indirect evidence. If another universe collided with ours in the distant past, it might have left a scar in the cosmic microwave background, a cold spot, or an asymmetry in temperature. Observations from the Planck satellite have revealed anomalies, like the so-called axis of evil, a strange alignment in the large-scale structure of the universe that shouldn't exist in a perfectly random cosmos. Are these just statistical flukes? Or could they be fingerprints of a prior universe or a neighboring one? We don't know. But the search continues. Future missions, like the upcoming Spherex and Lightbird satellites, will map the sky with unprecedented precision, hunting for subtle patterns that could betray the influence of something beyond our universe. Another radical idea comes from loop quantum gravity, a theory that reimagines space-time as a network of tiny, discrete loops. In this view, space isn't smooth, it's granular, like fabric woven at the Planck scale. When applied to cosmology, this leads to the Big Bounce theory. Instead of a singularity, the universe reaches a maximum density and then rebounds. Our Big Bang was not the beginning, but the aftermath of a previous universe collapsing. Think of it like a spring. Compress it too far, and it doesn't break. It snaps back. In this model, time extends before the Big Bang, but the laws of physics remain intact. The bounce is governed by quantum geometry, not infinite densities. Simulations suggest that information from the previous universe might survive, imprinted in the distribution of galaxies or the polarization of light. If true, the universe has no beginning, only an eternal cycle of contraction and expansion. But perhaps the most mind-bending possibility is that the universe came from nothing. Not empty space, not a void, but true nothing. No space, no time, no laws, no quantum fields. How could something come from nothing? Quantum mechanics offers a clue. In the vacuum of space, particles flicker in and out of existence due to quantum fluctuations. These are not violations of energy conservation. They're allowed by the uncertainty principle. Some physicists, like Lawrence Krauss and Alexander Vilenkin, have argued that the entire universe could have emerged from such a fluctuation in a primordial nothingness. Vilenkin's tunneling from nothing model describes the universe appearing like a bubble in a quantum foam, with zero total energy, positive energy in matter balanced by negative energy in gravity. In this view, the universe is the ultimate free lunch. But critics argue, if there's a quantum vacuum, is that really nothing? Doesn't it require pre-existing laws of physics? The debate hinges on what we mean by nothing, a question that blurs the line between physics and philosophy. And that's the deeper truth. The mystery of what came before the Big Bang isn't just a scientific puzzle. It's a mirror held up to human curiosity. Every civilization has told origin stories. Sumerian, Hindu, Aboriginal, Norse, each reflecting the limits and insights of its time. Today, we tell our story with mathematics and telescopes, but the impulse is the same. We are pattern-seeking creatures, driven to make sense of existence. And in that search, we've discovered something extraordinary. The universe is not static. It evolves. It has a history. And we, stardust, self-aware, fleeting, are part of that history. The iron in your blood was forged in a supernova. The oxygen you breathe was exhaled by ancient stars. You are not separate from the cosmos. You are the cosmos awakening to itself. So where does that leave us? With more questions than answers. With theories that push the edge of imagination. With data that hints but doesn't confirm. But also with tools more powerful than ever. The James Webb Space Telescope peers into the first galaxies. Gravitational wave detectors listen for ripples from the dawn of time. Artificial intelligence scans the sky for anomalies we might miss. And theoretical physicists continue to refine models that could one day unify quantum mechanics and gravity, perhaps revealing a deeper structure beneath reality itself. We may never know what came before the Big Bang, or we might. The history of science is full of moments when the impossible became obvious. The Earth orbits the Sun. Light is both wave and particle. Time slows near a black hole. Today's speculation could be tomorrow's textbook. So we keep asking, we keep looking. Not because we expect final answers, but because the act of questioning is what makes us human. If this journey has stirred something in you, if you feel that pull toward the unknown, don't let it go. Explore, read, question. The universe is vast, ancient, and full of secrets. And the most profound discovery may not be what happened before the Big Bang, but the realization that we, fragile and temporary as we are, can even ask the question at all. If you want to go deeper, subscribe to this channel. Join the conversation. Because the search for origins isn't just for scientists, it's for everyone who looks up and wonders. And the story is far from over.